Hello and welcome to TidyX episode 181. TidyX is a screencast where we go through and explain how our code works. My name's Ellis Hughes.
And my name's Patrick Ward. Thanks for talking to us or meeting with us today, I guess. TidyX episode 181. Title is I Likert Coffee. We're going to be talking about coffee
Hey,
and
hey.
Likert scales and analysis because, as my mug says, it's always a good time for statistics. So this is it's amazing. This is some Tidy Tuesday data from May 14th, and it's some coffee kind of Likert scale grading data, right?
Yeah.
Um,
So first,
yeah.
I guess what are we trying to figure out here? What is Likert for the first part for
Okay, like
for
I
our
believe it's
viewers?
actually Likert,
Likert?
but
Ah,
it's a traditional way that's been used in psychology of rating things, usually on some range of agree to disagree or like to, dislike or to strongly like, type of scales.
or like rate it from like 0 to 10 or something like that in
Yeah,
some sort of.
usually they're on some sort of odd number scale, so there's no true middle, like a 1 to 7 or a 1 to 5. And they're integers, right? There's often not halves or points in between. They're usually just single digit numbers, and they're bounded. So 1 to 7, you can't have an 8, and you can't have a 0. You have a 1 or 7 or any of the integers in between. And so there's lots of debate on how you analyze these things and look at them, and it's not really settled, and there's lots of disagreement. But with this coffee data, I thought since over the past couple episodes we've been talking about things like for loops and functions, this would be a great one to basically take some of that coffee data, grab one of the variables, in this case, expertise. You're rating your coffee expertise, and we're rating it based on the age classification of the people. So we have groups. We have one, two, four, six. We have 7 different groups of age, and they're going to be rating their coffee expertise. And what we want to do is analyze the difference in expertise between these groups. And we're going to use a for loop to help us do that and make every single possible planned comparison across these 7 these 7 age groups. So if we run this, we'll get our filtered coffee.
So you could say we're taking our coffee, grinding it down, filtering it, and brewing out some data.
There you go.
So we're going to load in the data from TidyTuesday from just the straight URL here using readr read CSV. We're going to take coffee, filter it to remove any cases where age is NA or expertise is NA, and we're going to just pull out those two values, age and expertise, and then we're going to apply a factor to it. And so this is now going to convert age from a string into a factor where ordering of these strings actually matters. So it's less than 18, 18 to 24, 25 to 34, blah, 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 all the way up to greater than 65 years old. So we now have all those groups and we just have age and expertise. So this individual is 25 to 34 and rates their expertise as 7 or less than 18. And apparently,
Oh,
what,
they're up.
Dunning-Kruger, right?
They're very confident
Yeah,
in their coffee expertise, I
which
suppose.
I mean, maybe they are, but okay.
Mhm.
um, so now we're gonna, look at that. Okay, what is the distribution though of coffee experience? Let's just do like a quick look at what's going on here. So we're gonna take our filtered coffee, do a count by expertise. So this is just gonna give us there are 37s, there's 3 10s, there's 6 6s. I don't know.
Yeah.
And then throw it into a ggplot. We're going to say, hey, actually, as factor expertise, and that's going to put it into the scale of alphabetical, I believe it's because it's numeric. And then y is going to be n. And then we're going to throw a genome call so we can actually do columns. So you can see here, we've got a few ones, but like the vast majority, it's kind of skewed to the right a little bit, but then it tails off pretty quickly. And because obviously you can't go higher than 10. So a lot of people are thinking they're like better than average if 5 is average.
Yeah, this is not uncommon in Likert scales to have the distribution shifted towards one side of the scale or the other. Rarely is it set directly in the middle.
Hmm. But what does this look like if we then stratify by age? Does this same thing hold? Is it as you get older, you get more retrospective and really understand, what your true expertise is, or what does how does age actually impact expertise? So we're gonna take our filtered coffee. This time we're not just counting by expertise, but also age. We're going to then again factor expertise, geom call again, so we get the columns. But this time, so we're going to do a facet wrap by age. So this is going to then do a different facet for every single age group that we have here. And because age is already factored, we get a situation where it's going to then order them in the order that we have the different factors in. So less than 18, 18 to 24, blah, 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 all the way up to greater than
You can
65.
see the sample sizes are a bit thin in some of the age groups. You could set your scales to free Y. You just probably want to put in your plot title that note the Y values are on different scales, but
Yeah, because this
because
one it looks like, oh, actually 18-year-olds were actually breeding themselves, maybe not as expert
yeah,
compared to 35, 34-year-olds. But again, it's kind of hard to tell.
yep, yep.
So then what are we going to do next, Patrick? This is another plot, but how are we doing this? How is this next plot different?
Well, one of the ways that so this one here is actually because they're on different scales. If you didn't want to use the scales equal free, I'm just going to do a bit of sampling with replacement. So I'm going to upsample everybody, or not upsample. I guess some of the groups will be downsampled, but I'm going to sample everybody to 1,000 values with replacement. And so the idea here is that I'm plucking 1,000 people. They can come back in once they've been plucked, but I'm plucking 1,000 people from each of these samples, these stratified age samples here, so that I can build up a possible population distribution, and everybody's now on an equal scale. And then we're just going to use the same geom call function here. So now we get a look, and it looks relatively similar. The distributions look relatively similar to what we saw on the previous slide, as they should, but you can now see that the y-axis is the same for everybody. And these are the theoretical distributions of the population, assuming that we had random sampling and all that jazz. And then the final piece is often with these Likert scales, because they are integer type data, one way people look at them is using things like the interquartile range. And so the box plot helps us do that. So remember, the box represents the interquartile range, which is the bottom 25th percentile and the top 75th percentile, with the black line in the middle being the median. And then the stems are just reaching out to any outlier points, or points outside, sorry, of the interquartile range. And then we have some outliers where there's a few ones in the 45s and the 35s and the 25s group. So we can see from this very clearly that the median expertise level of that sort of middle-aged crowd appears to be higher than the youngest crowd, and it appears to be higher than the oldest crowd. And the youngest crowd, median on average, appears to be the lowest group in expertise, which we would expect because they probably drank the least amount of coffee and probably have the least amount of funds to buy good coffee. So there's that as well. Their palate isn't as refined. We can, of course, summarize this data in terms of the quartile range here. We can summarize it in different ways. So here we're going to group by age. We're going to get a sample size for each group. We're going to get the mean and the standard deviation of expertise. We're going to get the middle value, which is the median, and the median absolute distance. And then we're going to get the interquartile range, the 25th percentile, the 75th percentile, and then the actual IQR itself, the difference between the 75th and 25th percentile. We just print that out into a nice little table here. And so again, just a different way to compare these things. And we can see that the middle values, the median values, are integers representing the data. which is different than what we see in the average, which is the arithmetic average, which is not an integer. Yeah. Okay. So let's make some comparisons between these groups. Let's say we're really interested. Our boss comes to us and says, gosh, I really want to know if there's any meaningful differences in coffee drinking expertise between these 7 age groups that we have. So let's, for example, one way to do this would be to do a t-test, which is comparing the means and the variances of the 2 groups. So we're comparing the means, we're taking in the mean and the variance of the 2 groups. We're comparing those groups and we're trying to understand if there's a difference between those 2 that is meaningful. In the case of the t-test, it's asking the question of whether there is a statistically significant difference between group 1 and group 2. In this case, group 1, we have 18 to basically the 18 to 34, or what is that? Filtered coffee.
Yeah. So it's the 18 to 24 versus 25 to 34-year-olds,
Yep,
but you're
that's what we're
comparing
comparing.
expertise by age.
Yep. And so we have our 2 groups here. If we run this, we get a result, and we have our 2-group comparison. We have the means of the 2 groups. We have the 95% confidence interval around the difference between the 2, 5.74 minus 5.44. And then at the top, we have some information about the test itself. We have the t-value, which is 2.8, which is going to be much larger than 1.96, or probably with this sample size a little closer to 2, which means that we're going to have a statistically significant result, which we do. And then we have the degrees of freedom calculated, which is basically baking in the sample size of group 1 and the sample size of group 2, and that's the information basically about the test. So what if we wanted to do this at scale? It would really be a bummer to try and do that t-test for every single comparison possible. It'd be
You
a
want to
lot
write
of
that out,
copy
right?
and pasting. What's that?
You want to write that all out, right?
Yeah, no, it'd be a lot of copy and pasting. It would be a lot of potential for error, right? Because
Mhm.
of all the copy and pasting. So let's make the computer work for us. And we're going to do this in a for loop. So the first thing that we do is we are going to get all possible comparisons of the unique groups, of the unique age groups. So here I have group 1 is the unique age groups, and group 2 is the unique age groups. And we pump this into that expand grid function, or crossing would be another function in tidyverse you could use. But basically what this does is it gets us the Cartesian product. It gets us every single possible permutation of each of those group relationships. And then the last thing that I do is I filter out anytime group 1 is equal to group 2, because we obviously don't need to make a comparison between 2 groups that are the exact same group. There's 0 difference
What's the
between them.
point?
What's the point? So now we have a cool table, right? Wait a minute. We don't, because we took unique from the age group for group 1 and the same unique for the age group for group 2, we have a possible situation where we get flip-flops. For example, if we look at when group 1 is less than 18 and group 2 is 25 to 34, we get the same group when group 1 is 25 to 34 and group 2 is less than 18. These are the same comparisons. We don't need to do this. We don't want to do this. So I came up with a little bit of a way that we could sort this out. Ellis, why don't you walk us through what's going on in this code to help us get rid of any duplicates?
Yeah, so we're going to use a simple kind of dummy example that just has ABCs to compare each other, but this sort of idea kind of expands out to cover more situations where you do have you're trying to do an expand.grid, or expand grid, but also trying not to duplicate the same comparison again and again. So we're going to say R is A, B, and C, and we're just going to turn it into a quick factor for us just to make our lives easier. Those are B, C, A. We're going to apply that same expand.grid that we did, like Patrick did earlier for our comparisons of age. And again, we're going to filter out any cases where they are identical. So you can see here, we've got B compared to A, C compared to A compared to B, C compared to B, A compared to blah, all the way down. So cool, we've got our set, but we still have that same problem where we have B compared to A here, and then we have A compared to B here. Those are the same, that is the same comparison, right? So what could we do? So let's do a sorting of each row and get out the same order, right? So that way it is A is always listed first, or excuse me, it would be because it's BCA. B is always listed first, then C, then A. Always. So the two comparisons are then gonna always match. Right, and we can see here what's done is, and let's look at a transpose because it's a little bit easier to see. It's now going to take A and B, and then it's going to have A and B here as well, which is matching these orders here. B and C, A, C, B, C. So once we have that, what we can actually do is now they're all in the same order because we actually don't particularly care which group, what order they're in. Like comparison of 1 versus 2. The order for us in our t-test doesn't matter. There might be situations where it does. This situation, it doesn't matter. So we can do this sorting and go, hey, any case where this is duplicated, so the first and second entry, so here we can see 1 and 3 are the same, or 4 and 6 are the same, knock them out. And so we can do this duplicated test here. So this is just kind of building up this logic. We call it duplicated. So false, false, true, because this is the second time this appears. False, true, true, because AC appeared here and BC appeared here. And so then we can just invert that to say, okay, these are the cases we want to keep are not duplicated. And so now we can just apply that in here to RFDF. So say keep all the cases where they're not duplicated, or all the rows that are not duplicated, and we end up with only these 3 comparisons because those are the 3 comparisons that are unique for our situation. And so we can apply that exact same logic to now scale up to our age group comparisons, again saying I don't care if it's less than 18-year-olds to 18 to 24-year-olds, or 18 to 24-year-olds versus less than 18-year-olds. I just want one of those. And so apply that here to comps. And now we have totally unique 36 comparisons as opposed to the number that we had before. And now we can also just verify that our code actually did what we think it does by making sure that these two comparisons, or this sort of comparison, only gives us 1 row. And it does. So cool. We've now removed all the duplicate comparisons, so we can just move forward with that. So now we also have to figure out what are the, actually Patrick, tell us what do we want to pull out of our t-test then to store for later information?
Yeah, so you can see the t-test result that we ran above gives us a whole bunch of information, and we don't need it all. And we want to store our results in a data frame. So if we call names on the element of our t-test, oh yeah, we want to see what it is. What is that?
So
Some
this is
sort
the
of
structure. So this is
oh, yeah.
all, like, if you, rather than you just calling names, if you call the structure, this will tell you all the information it can about
Mhm.
the object.
Yep. And we only want certain pieces of this structure. So we're going to decide on what we want. We probably want to get the difference between the groups. We'd love to get the 95% confidence interval, and we'll snag the p-value as well. So we're going to write a for loop to do this. The only thing that we need to be aware of is we've got multiple comparisons. We got 36, 20. I can't remember how many comparisons.
36.
36. I don't know why I wrote 21 there. So we're going to correct for this. So when you do multiple comparisons, you need to guard against a type 1 error. And one of the ways that people do this in frequentist statistics is they will
Ah,
we got all kinds of stuff going on here.
look out! Don't worry about it. Pay attention to my hands over here.
Yeah, right. One of the ways that people do this in frequentist statistics is to adjust the p-value to correct for multiple comparisons, because it's easy to just by random chance, if you have 36 comparisons, for example, find something that's statistically significant and declare that your study was indeed a success. So the way that you do that is you set the alpha level that you're interested in. In this case, we'll choose the common convention of p 0.05. And we have our number of comparisons, which is going to be 36. And the
20.
Bonferroni correction, no, it is 21.
Huh.
Yeah, there you go.
Did
The
I
Bonferroni correction
did something wrong then?
is the Bonferroni correction is a very simple correction to the p-value, where you're basically doing alpha divided by the number of comparisons, so 0.05 divided by the number of comparisons, and then you take that value and you do 1 minus that value. And that gives us our adjusted p-value for the number of comparisons we're trying to make. In this case, it's going to be very close to 0.999. Okay, let's set up a storage data frame so we can store the results of our t-test for loop. Again, we're going to have our group 1 and group 2 in this storage data frame. These are the groups we're comparing. And then as we stated above, we want a difference between them. We want the low confidence interval 95%, the high confidence interval 95%, and the p-value. So now we have a nice little data frame. We can take ahead of that and we can see that those are all empty and they're just waiting to be populated by this cool for loop, where we're going to do for every I iteration in 1 to the number of rows of comparisons, which is 21, we're going to run the t-test. And so this is exactly the same t-test that we ran above. We're filtering the age in the groups of group 1 and group 2 of that multi-comps data frame that we've created. And then we're going to do a t-test where we're comparing the expertise by age. And the confidence level here is our Bonferroni correction. And then we get the results of that t-test and we store the elements from the t-test structure that we care about. So the estimate of group 1 and the estimate of group 2, the difference between them is going to be the difference. That's what we store in column 3. In column 4, we store the low confidence interval, so confident 1. And then in row 5 or in column 5, we store the high confidence interval, so confident 2 from the t-test function.
So folks can see it.
Yeah, it's going to give you a little vector there. So we're just calling the elements of that vector. The p-value, obviously, we take that out, and if we did estimate as well, we would see that it's the same. It's going to be a vector of 2 for group 1 and group 2. And so then we're taking the difference of those. So if we run this for loop, it's going to run super fast because there's not a lot of work that it has to do. And it's already done. And now we see we have a whole data frame of all of the comparisons with the confidence intervals and the adjusted p-values. And so we can simply...
Are these adjusted p-values or are these raw p-values?
Those should be...
The confidence level is adjusted, but is the p-value
Oh,
changed?
you're right. I believe it. That's a good question.
I don't know. This is not stats person talking here.
I'd have to figure. I think I know it adjusts the confidence interval, but that's a good question. I don't know if it adjusts the p-value if you change
confidence
the
level of the interval.
Of the interval. Okay, so those are unadjusted p-values, and that's why we want to do any of them less than our
Yes.
Bonferroni correction. So when we filter this out, I think we have 5.
Yep.
Yeah. So the age, the 65 and older crowd looks to be higher in expertise than the 25 to 34 crowd. 35 to 44 and the 45 to 54 crowds look to be higher than the 65-year-old crowd. The 35 and 44 look to be higher than the 18 to 24-year-old crowd, and the 55 to 64 look to be higher than the 35 to 44 crowd. So that's one way to do this. There's another way to do this, to take those p-values, which Ellis showed me this morning, and I've never seen in all my years using R.
Despite us doing TidyX for 4 years.
Yeah, well, so why don't you talk us through what we have here?
For sure. So we're again taking those multiple comparisons data frame out there, but rather than doing this just straight up filter for the Bonferroni correction, which is any p-value that's, I mean, there's a couple different ways I guess you could technically do this, but we're just saying anything that's less than our Bonferroni correction, or 1 minus it. We're going to keep that. But what if you actually wanted to keep your adjustment of your p-value? So you could maybe look at a distribution. My background where I've looked at statistical genetics, or supported people that did it, and those comparisons are in the thousands to millions of p-values, and so don't really want to do a Bonferroni correction for this. Also, it's a lot easier because maybe we want to keep the raw value. We also want to know what the adjusted p-value would be. And so the way that this is baked into R, at least, is there's this handy dandy function called p.adjust, which you feed in the vector of your p-values and you say, hey, adjust this by some sort of method. And R comes baked in with a whole mess of different types of adjustment methods. So Holm, Hochberg, Hommel, Bonferroni, which is the one we're using here. Benjamini and Hochberg, I believe, is that one. BY is Benjamini and Yekutieli, I think. Um,
And there's different
Hochberg.
ones as well. Tukey, the different corrections have different kind of levels of penalization. Some are more conservative than others.
Yeah,
So, if you're doing thousands of comparisons, you probably want to be as
it's
conservative as
strict.
possible.
Yes,
Yeah,
because
very.
essentially you're p-value fishing, right? You're like, hey, I'm going to do all these comparisons because I don't know which one I want to C is giving me a statistically significant result. But because by setting our alpha value to 0.05, there's a 5% chance, and this is, of course, non-stats person talking here explaining p-value, so very, very helpful. But there's a 5% chance that your analysis is going to be giving an incorrect result, or there's a 5% chance that it's not actually significant is my understanding of this. So by doing this p-value adjustment, you are penalizing for having done a bunch of comparisons at that whatever level that you're trying to say is significant, and trying to correct for that. And so we get the same results because we were ending. Bonferroni is a very standard comparison here, but you can see how the adjustment where the less greater than 65 versus the 25 to 34 year olds had a pretty low p-value, but we adjusted. It still would be significant. It is still significant, clearly at the zero point
Yeah.
zero 0.05 level, but it's not as obviously if you're trying to make decisions based off of p-values.
Of course, if you change the adjustment method to, let's say, BH, you might get different, results. So
Get
we get
more
a few more observations that are put in there.
Benjamini Ectielli.
Yeah. So
But it
different
makes it really easy to change the way that you're adjusting your p-values. Again, you should have decided that ahead of time, but
right.
um, if you need a function to do it in a variety of different ways, this is a very easy way to do it. Um, so yeah, I really like root coffee.
Yeah, there we go. I mean, that's some kind of overview on we've been talking about over the past few episodes using for loops and functions to do some of the heavy lifting for us so that we don't have to get into a whole bunch of copy and pasting type of stuff.
Hey,
So if there's more things that you'd like to see from loops and functions, comment on the episode below and let us know.
cool. With that, thank you all so much for joining us for 181 episodes of TidyX. As always, my name's Ellis Hughes, and you can find me on various social media sites at Ellis_Hughes.
And my name's Patrick Ward. You can find me on X at OSP Patrick at tidy_explained is where the screencast does live on X. Of course, easiest way to hit us up is on the YouTube channel. Questions, comments down below. We'll try and get back to you. Maybe one of your questions becomes an episode in the future. And as always, if you enjoy the work that we are doing, you feel like it's helped you in some meaningful way, and you'd like to donate to the show, we do have a Patreon, and we're grateful for anything that you may want to give.
Thank you all so much, and keep on exploring your world.